Welcome back, ladies and gentlemen. Today we're going to talk about climate. So, when we talk about dividing the globe, the biosphere, into things like biomes and ecosystems, that is taking into consideration both the abiotic or the non living components of that portion of the globe, as well as the biotic stuff. So, if we're going to talk about the sort of living things and the adaptations that would exist in those different biomes or ecosystems, a lot of that is tied back to the climate. So when we talk about climate, we're talking about these long-term patterns of weather in a region. So average temperature, average precipitation, relative humidity, are there seasons, that kind of thing. Don't confuse weather with climate. They are not necessarily the same thing, although they are certainly related to each other. So when we talk about weather, we're talking about day-to-day patterns. Today is sunny and we're expecting a high of 45 degrees. That kind of thing is weather. When we talk about climate, we're talking about long-term patterns, so over months, years, decades, longer than that. What are the average conditions we typically see in that particular region? So that climate really is a distribution of this uneven heating of Earth. So when we look at Earth as a globe, it's a sphere. And that Earth is not only rotating on its axis, but it's also revolving around the sun. And so the angle at which that sun's direct rays are hitting the Earth, there's a differentiation in terms of that direct hit. So when I look at the entire globe, we really end up breaking Earth into three major climate zones based on how much direct sunlight is hitting Earth. So when I look at the equator, that's going to get the most direct sunlight. And as we get further and further towards the poles on either end, the angle at which that sun is coming in isn't hitting at a 90-degree angle. It's going to be lower and lower and lower as we move towards the poles. And so that angle has a lot to do with the weather patterns and the climate that we end up seeing in regions like that. So let's talk about those different zones. We look at the tropics, and this is going to hit between approximately 32.5 degrees north latitude, what we know as the Tropic of Cancer, and about 23.5 degrees south, or the Tropic of Capricorn. So we're talking from here's the Tropic of Capricorn, here's the Tropic of Cancer, and within that is considered the tropical regions. This is the warmest temperature zone, mostly because it receives the most direct sunlight. This is where we don't generally see a whole lot of seasonality. It's kind of springish, summerish all the time. And that's simply because Earth's rays are coming in at the closest to 90 degrees that we can experience. When you look directly at the equator in the middle of those two, that's where we're hitting at 90 degrees. Your polar regions then are either up here in the Arctic Circle, which is above 66.5 degrees north latitude, or down in the Antarctic Circle, 66.5 degrees south latitude. These are the coldest temperature zones because they receive the least amount of direct sunlight all year long. And in fact, there are certain portions of their year where they are just totally dark for 24-hour periods because of the way that the angle of Earth tilts. It's not rotating directly up and down, right? So our rotation here is on an angle of 23.5 degrees. And so that's where we end up getting this unequal distribution. And so there is some sunlight at the poles, just not necessarily a very direct angle like we see at the equator, and such a low angle, to be more specific, that there are certain portions of their year that are completely dark. The reverse is also true, though. Then there are certain parts of their year which are completely sunny for 24 hours, which is kind of crazy to think about. We sit here in the temperate zones. So between that tropic tropical zone, and the polar zone is the temperate zones, which is what you are used to. This is where we experience those seasonal changes. The closer you get to the tropics, the less extreme those seasons become. And the same thing could be said at the closer you get to that Antarctic Circle. So we are sort of almost directly sitting in the middle of that temperate zone, and so we see the biggest shift in our seasons in terms of going to that very cold winter that we're used to, as well as those really sort of warm temperatures we see in the summer. So not as extreme heat as we might get in the tropics, not as extreme as the cold we would see in the polar regions, but we are sitting somewhere in between that. So that unequal distribution of sunlight, and as a result, unequal distribution of heat and radiant heat that comes from those sun rays, ends up setting up these really interesting wind and precipitation patterns at the equator, and then these get recycled as we get closer to the poles as well as closer to um, further away from the poles. So the warmest air masses are near the equator, right? This is where I'm getting direct sunlight hitting the earth, warming up that air. Now, if you know a little bit about weather and just moisture and air currents, the warmer the air, the more moisture it's able to hold. And as a result, that moist, warm air ends up rising to the surface, or rising up, I should say, in the atmosphere. And as it does that, it cools off. So the further and further I get into the higher atmosphere, the cooler and cooler the temperatures become, which means that warm, moist air gets cooler and cooler, which means it can hold less and less water. So as that temperature cools, it ends up dropping rain, right? And so we end up setting up what we call these convection currents. So as that dry descending air gathers moisture from the surface, rises into the atmosphere, it drops all of its water because it can't hold as much, right? Temperature's going down. And so we set up these convection currents. If any of you have a convection oven at home, it's a very similar idea in the sense that we're wrapping this moisture and wrapping this air in your oven to try and cook your food quicker. Um, what this does set up, though, are these really interesting air masses at the tropics, right, where we've got lots of temperature and lots of moisture. And so we're dumping a lot of moisture there as a result. And as that all that moisture gets dumped at the tropics where the heat is the highest, that dry air then moves up in latitude or down in latitude, depending on whether you're going north or south. And we get these very arid regions sitting at the edges of these convection currents. So as that air gets drier and drier and drier, it ends up becoming less and less dense, and that's why it falls again. So when we look at your tropical regions, right, where we typically think of lots of rain, lots of moisture, um, that's the reason that sits there. But we go just above that, somewhere around approximately 30 degrees north latitude, 30 degrees south latitude, are where we see some of the world's largest deserts. And that's because we're getting all of that dry air to kind of dump back down. That's when it's at its driest. It'll come back over those land masses or water masses for that matter, and pick up that moisture again, dump it all over the tropics of the equator, where we typically think of things like rainforests, and then dry off again. So places like here in Africa, where we've got the Sahara Desert, or when we look at up here in the U.S., we're sitting somewhere around that again in places like Arizona and Nevada, where it's much drier. Um, and that's because of these convection currents that are being circulated because of the direct solar radiation causing this to happen to the air in the atmosphere. So above and below 30 degrees, that air moves again, produces a lot of the rainfall that we then end up seeing in temperate zones. So why do we see those general seasons here and we see a lot of rain in things like spring and fall, or all the snow in the winter? It's again because we're sitting um, at that sort of temperate zone where we're very much looking like this all over again. And then you get high up into upper Canada and just outside of the polar regions. And again, it's now these Arctic deserts where it's much cooler and much drier up at that end of the globe as well. So not only does the direct sunlight cause those wind and precipitation patterns, but we also see this in other components as well in those wind patterns. So we see those general big convection currents up in the atmosphere, setting up places like the deserts, the rainforests, our temperate zones. But we also see some other interesting wind and, as a result, ocean currents that gets set up by that direct sunlight as well, or lack thereof. And so we look at sort of these westerly winds, or why do we have the jet stream where we do here in the US? If you watch the weather, they talk about the jet stream moving across the oceans. We look, or I should say, across the continent. We look at the oceans and we see a lot of interesting currents that also get set up. So when we look at any sort of current, we're talking about some sort of river-like flow pattern within a body of water or within air masses. And those currents are moved because of differentiation in temperature, which is a result of the different amounts of direct sunlight that hit the globe. So you hear them talk about the Gulf Stream, right? So it picks up all of this warm air here in the off the coast of Florida and the Caribbean, so on and so forth. And as that water moves up further and further and further, it will eventually cool off and drop. And so it'll sink. And so it'll move back again. So we get those convection currents in the water in our oceans, just like we were seeing back here with the air masses. So the warmer water sits at the top, cooler water sinks, and we get these convection currents there as well. And that's a really big deal because this is what moves some of that colder water away from the poles. So if you look, most of them are shooting down, all those blue arrows, those cold currents. And then those red currents are moving towards the poles. And this just kind of keeps an evening of temperature. We start shutting down these currents, whether they're air masses, whether they're water currents, we get into some serious trouble. Something I will throw out there while we're talking about this is not only when we talk about oceans are we talking about temperature, but we're also talking about salinity. So the warmer water can hold more salt. Cooler water holds less. So as these warm currents come up into the poles, they lose their salinity as well as their temperature and sink and move back down. So that becomes a really big deal when we start talking about all of the polar ice melting. It's all fresh water dumping into the ocean. So not only are we worried about just rising temperatures messing with these currents, but we're also concerned with the fresh ice that is melting off the poles, dumping all of that fresh water into the oceans, causing it to be less salty, which is also disrupting these currents. And so why is it such a big deal? Well, take a look at us. So we're here, give or take, right? And you're used to the climate that we see here in Pennsylvania. Go over to places like Great Britain, and if you look, they are at a much higher latitude than us, and yet their climate is much more similar to us than what they might see more in line with others at their latitude up in the middle of Canada, right? So we're talking like polar bear country up here. So why is that? Well, the Gulf Stream comes up along the coast of the US, but also ends up dumping over here in Europe. And so that's going to provide them with a much more temperate climate similar to ours. If this were all to shut off, this would get really, really cold really, really fast. And that's not something that our economies or our infrastructures or anything is set up to deal with. And so when we talk about global warming and climate change, it really is climate change. So although the general temperatures of Earth are getting warmer, collectively it is climate change in the sense that we are seeing much more extreme seasons here in Pennsylvania. If this were all to shut off, we would see much more fluctuation in colder temperatures here in places like the UK. So we're seeing bigger swings in climate patterns than we have historically experienced, at least within human lifetimes. And a lot of that is because not only do those global temperatures affect the wind patterns, they affect the currents, they affect a lot of things. If we go across over to Southern California, places like LA, San Diego, they have much more consistent cooler temperatures than we might experience here, because they actually have a current coming down from up here in Canada and it's cooler. So if you've ever stepped into the Pacific Ocean, it is frigid. And it's because all of that water is being dumped from up around places like Alaska, where it's much cooler. So we've been talking about the fact that this disproportionate sun ray angles causes seasons, at least in the temperate zones, right? And those changing seasons really are due to the fact that Earth doesn't sit completely up and down, right? When we take a look at the axis by which we rotate on, it isn't straight up and down. Instead, it's at a tilt, right, at 23 degrees, 23.5 degrees, okay? So that means that the distribution of those convection currents in the atmosphere, the wind, the water, all of that gets shifted a little bit every time that we revolve around the sun while we're rotating on that tilted axis. So those belts, if you will, if you want to think of them that way, of wet and dry air straddling the equator shift up a little bit into the northern hemisphere when we experience our summer. They shift a little further down when we experience our winter. And a lot of that has to do with this tilt of 23.5 degrees.
When I was a kid, my understanding of the seasons was that December and January were cold and covered with snow. April and May were bursting with flowers. July and August were hot and sunshiny. And September and October were a kaleidoscope of colorful leaves. It was just the way the world worked, and it was magical. If you had told me back then that 1/3 of Earth's population had never seen snow, or that July 4th was most definitely not a beach day, I would have thought you were crazy. But in reality, seasonal change with 4 distinct seasons only happens in 2 regions on the planet, and even in those 2, the seasons are reversed. But why? A lot of people have heard of an astronomer called Johannes Kepler and how he proved that the planetary orbits are elliptical and that the sun is not at the center of the orbit. It was a big deal when he figured this out several hundred years ago. His discovery solved a lot of mathematical problems that astronomers were having with planetary orbit measurements. While it's true that our orbit's not perfectly circular, those pictures in our science books, on TV, and in the movies give an exaggerated impression of how elongated our orbit is. In fact, Earth's orbit is very nearly a perfect circle. However, because Earth's orbit is technically an ellipse, even though it doesn't look like one, and the sun isn't quite exactly at the center, it means that our distance from the sun does change through the year. Aha! So winter happens when the Earth is further away from the sun. Well, no, not so fast. The Earth is actually closer to the sun in January than we are in July, by 5 million kilometers. January is smack dab in the middle of the coldest season of the year for those of us up north. Still not convinced? How about this? Summer and winter occur simultaneously on the surface of our planet. When it's winter in Connecticut, it's summer in New Zealand. So if it's not the distance from the sun, what else could it be? Well, we need to also know that the Earth doesn't sit straight up. It actually tilts. And that axial tilt of the Earth is one of the main reasons for the seasons. The Earth spins on an axis that's tilted 23.5 degrees from vertical. At the same time, the Earth revolves around the sun with the axis always pointing in the same direction in space. Together with the tilt, the spinning and revolving causes the number of hours of daylight in a region to change as the year goes by, with more hours in summer and fewer in winter. So, when the sun is shining on the Earth, it warms up. After the sun sets, it has time to cool down. So, in the summer, any location that's about 40 degrees north of the equator, like Hartford, Connecticut, will get 15 hours of daylight each day and 9 hours of darkness. It warms up for longer than it cools. This happens day after day, so there's an overall warming effect. Remember this fact for later. In the winter, the opposite happens. There are many more hours of cooling time than warming time, and day after day, this results in a cooling effect. The interesting thing is, as you move north, the number of daylight hours in summer increases. So Juneau, Alaska would get about 19 hours of daylight on the same summer day that Tallahassee, Florida gets about 14. In fact, in the summertime at the North Pole, the sun never sets. Okay then, it's all about daylight hours. I've got it. Well, no. There's another important piece to this puzzle. If daylight hours were the only thing that determined average temperature, wouldn't the North Pole be the hottest place on Earth in northern summer? Because it receives 24 hours of daylight in the months surrounding the summer solstice. But it's the North Pole. There's still icebergs in the water and snow on the ground. So what's going on? The Earth is a sphere, and so the amount of solar energy an area receives changes based on how high the sun is in the sky, which, as you know, changes during the day between sunrise and sunset. But the maximum height also changes during the year, with the greatest solar height during the summer months and highest of all at noon on the summer solstice, which is June 21st in the northern hemisphere and December 21st in the southern hemisphere. This is because as the Earth revolves, the northern hemisphere ends up tilted away from the sun in the winter and toward the sun in summer, which puts the sun more directly overhead for longer amounts of time. Remember those increased summertime daylight hours? And solar energy per square kilometer increases as the sun gets higher in the sky. So, when the sun's at an angle, the amount of energy delivered to each square of the sunlit area is less. Therefore, even though the North Pole is getting 24 hours of daylight to warm up, the sunlight it receives is very spread out and delivers less energy than a place further south, where the sun is higher in the sky because it's more tilted toward the sun. Besides, the North Pole has a lot to make up for. It was cooling down without any sunlight at all for 6 months straight. So, as the seasons change, wherever you are, you can now appreciate not just the beauty of each new season, but the astronomical complexity that brings them to you.
Okay, so we can talk climate at big global scales, which is what we've been doing so far, but we can also zoom in and see how land masses also play a huge role in local climates. And those land masses tend to heat up and cool down more quickly than water. Think about it. We talked about the fact that water has one of the highest specific heats of all materials on Earth. So it can take in a lot of energy before it raises its own temperature. It can also release a lot of energy before it changes its temperature. Land, not as much water, and so we compare the cooling and heating of land masses to water, and clearly the land with less water is going to shift its temperature more quickly. So areas that are closer to bodies of water tend to have smaller changes in temperatures than areas when we go further inland, because that water can also set up its own little micro convection currents. So coastal sites tend to have higher humidity, more precipitation than areas inland. So let's use San Diego, for example, in discussing how this would work. So San Diego sits here right off the coast of the Pacific Ocean, and right next door are the Sierra Nevada mountains. Right on the other side of those Sierra Nevada mountains is the desert. So when we look at this, right, as air, cool air, moist air moves inland, right, it's going to dry off, it's going to warm up, it's going to hit those mountains, and it's going to rise. As it gets higher and higher elevations, the air starts to cool off again, and it sinks. So we get a lot of rain here on this side of the mountain as that air is rising, it's dropping its moisture, it's warming up, and it's rising into the atmosphere. Gets to a certain point where it can only rise so much, gets cool enough that it starts to sink. It tends to do that over the Pacific Ocean, if we're talking about San Diego as our example here, picks up moisture, comes back inland, and we keep these currents moving. And so those mountains often have what we talk about as a rainy side and a dry side. So here again, San Diego, Pacific Ocean, here's the Sierra Nevada mountains, and here is the deserts of places like Nevada. So those mountains, as that water comes in here, right, we picked up all that moisture, we start warming over land, we hit that mountain, it starts to rise up, we get all the rain, right? It gets dumped. We get some of those convection currents that continue to sit over here, but then you'll also get a lot of dry air that gets dumped on the other side of the mountain. So we talk about having a rain shield on this side, rainy side on this side, and then a dry side on the opposite side of the mountain. We can also dig even further down and talk about microclimates. So these are climates that are very specific to areas that vary from the more regional climate. Um, and we can talk about it in sort of very small regions, but a lot of times we'll talk about this within the context of things like underground burrows or in caves, where those climates might be cooler, damper, more humid, simply because they are more shielded from those direct sun rays. They're getting insulation from the dirt or the mountains or something along those lines. So this example is just the cute little kangaroo rats here who live in the deserts, but they have these sort of microclimates by burrowing underground to avoid that hot, dry climate where I burrow underground, I've got a lot more darkness, but also that means more moisture and cooler temperatures.